Okay. Let's go ahead and get started. I've got most of your exam graded. I still have a couple things I need to tidy up on my little grade report thing. So I have a feeling I'll have grades posted today. I might get your materials professor to distribute them tomorrow. Grades are going pretty much as expected. I mean, the grades I think are going to shake out pretty well. Just to put it in perspective, I think I have 5 of you that got 100. And one of you, it looks like, probably got a 99. You know what I mean? So, like, average at the end of the day is probably going to be like in the high 70s, maybe low 80s, something like that. So all in all, I think the class is going to do great. So I'm really not all that concerned about it. How did the concentrated moment homework go? Did that go well? Okay, good. All right. Today what we're going to do is we're going to tackle our last beam-related shear and moment diagram, which is shear and moment diagrams for beams with hinges, okay? And so we'll talk about how you address that. Before we do that, though, I'm going to take a little bit of an aside and talk about internal indeterminacy, because we haven't talked about that yet, for beams and frames, and how something kind of interesting happens with beams. So we'll get to that here in a bit. Before I go down the rabbit hole, though, did everybody get the QR code? Okay. All right.
Did Matt get the QR code? How did you get it?
He asked if you got it too.
Yeah.
He got it.
Okay, just making sure, bud.
All right, everybody get it? He's looking out for you. Yeah. Okay. All right. So there we go. Okay. So I'm going to blow through this first part really quickly because I think at this point you're probably sick of me saying this, but we are using the same relationship between load, shears, and moments, and we find the same conclusions being made for the graphical approach. The idea is that to develop a shear diagram, the relationship between loads and shears essentially says that we integrate the load diagram to get the shear diagram, and then we integrate the shear diagram to get the moment diagram. And in most cases, we can just use basic geometry to do that. Every now and then, we got to break out some equations if we have like a triangular load and whatnot, which is a good skill to have in general because it's nice to know how to derive those for deflections, or it's needed to be done. One thing I haven't talked about though is this related to beams and frames. So let's just get back into this headspace real quick. So for indeterminacy, so far we've discussed 2 equations. Okay, we have external indeterminacy, which is this, and then we have internal indeterminacy, which is this. And if you recall, really what we're doing here for these expressions is we're sort of taking the unknowns minus the knowns. That's essentially what we're doing, okay? So in the case of, let's say, internal indeterminacy for trusses, the unknowns are our support reactions, and then we have one unknown for every member, because truss members only carry axial load. So the unknowns in the system are M plus R, and then the known quantities are the fact that at every joint we have 2 equations of equilibrium, because there's no moments at a joint. So M plus R minus 2J is a means of computing the internal indeterminacy of trusses. Okay? For external indeterminacy, we take R minus the quantity E sub C plus 3. We know that for any system there are 3 equations of equilibrium, and we know that there are possibly internal equations of condition if we have hinges or some other internal release, although hinges are the most common. And there are also caveats to that. You know, reactions can't all be concurrent, can't all be parallel, etc. For beams and frames, the expression, we can sort of reason our way through that pretty easily. So this is a much more generalized expression of basically everything going on. In a frame, a beam or a frame type system, what are the unknowns? Well, we have an unknown for every reaction, and then for every member in the system, we have 3 unknowns. Not 1, but 3. Why do we have 3? Because for every member, we could have an unknown axial force, an unknown shear, and an unknown moment, okay? So the unknowns in the system are 3M plus R, okay? Now, the known quantities in the system are, bless you, are the the known quantities in the system are that there is a known for every equation of condition, so E sub C. But I propose for a frame or a beam type system, we don't have two unknowns at every joint, we have three, okay? Because the whole idea, the whole difference between a truss versus a beam or frame is that beams and frames can experience shears and moments, okay? So that means at the joints, there is a possibility of moment as well. So the unknowns in the system are 3m plus r, and the knowns in the system are 3j plus EC. That's your equation of condition for frames. Okay. Now I'm calling that I sub f. Okay. I propose that there is a very interesting special case that happens with beams. Okay. So a beam is really just a frame that's horizontal. Okay. That's really all a beam is, just like a linear frame. Okay. So let's just say I had, I don't know, a beam that looks like this. Okay. Okay. So I propose that this beam has one member and two joints. Okay, everybody with me on that? Okay. Let's take this beam down here. So let's put a support here. Let's put a hinge here. Let's put a roller here. Let's put a hinge there. Let's put a roller here. Let's put a roller here. Okay? So this is another one that's like a little bit more complicated. Okay? So how many members does this beam have? It has 1, 2, 3, 4, 5. And how many joints does it have? Well, for every, at the end of each member, what do we have? 1, 2, 3, 4, 5, 6. Okay, does that make sense? In fact, for beams, a simple way of saying it is that the number of joints is also equal to the number of members plus 1, right? Because if I take a beam, let's say I discretize it with 5 joints, right? 1, 2, 3, 4, 5 joints, 1, 2, 3, 4 members, right? There's always one more joint. Does that make sense? So if I wanted to, let's say, derive an expression, for I sub b, the internal indeterminacy for a beam, okay, I would say, let's say, what do we have? We have 3m plus r minus 3j plus E sub c, right? Okay. What I propose is let's replace j with m plus 1. Actually, that needs to be a bracket. Does that make sense? Okay. Now let's distribute this out. 3m plus r minus, okay, what goes inside these brackets? 3m plus 3 plus E sub c. Is that right? Okay. Let's distribute that out once more. 3m plus r minus 3m minus 3 minus E sub c. So the m's cancel. So we get r minus 3 minus E sub c, which is r minus E sub c plus 3, right? Well, that's the same thing as this. It's the same quantity. It just happens to work out that way, that the internal indeterminacy of a beam is just the same thing as this I sub e value. Okay? It just happens to work that way. Does that make sense? So that's how that sort of derives. The other thing I wanted to show you is, so if you check this out, this is the FE reference handbook. Has anybody looked at this yet? I hope you have. This is the reference handbook that you're allowed to control F during the FE exam, right? and it contains all of the formulas necessary for negotiating the exam. And it's bookmarked, so you have, for example, all of your math formulas, so you can get here and see all of your lovely trig identities and areas and volumes and derivatives and integrals and all that hullabaloo. And if you get to the civil engineering section, so you can see, okay, there's some stuff here that you probably haven't seen yet. For example, if you've never had geotech, then you haven't seen air, water, and solid phase diagrams for soils. Don't worry, you will. I can bring up the fluid section if you would like and show you all of the, here we go. We've got, you know, you want me to move on to another section, don't you? So, I love my job. Okay, but if you get to the structural engineering section, so let's look at structural analysis. Okay, I'm going to close this. I'm going to fit to width. Okay, so some of this stuff we haven't seen yet because we haven't gotten to it yet, like an influence line. We'll talk about that a little bit later. But some of this stuff should be relevant or familiar. For example, truss deflection by the unit load method. We've already done this, okay? So how do you compute the truss deformation? Okay, you take the sum of your little f times this term, which is big FL over EA. We've done that in here, right? So you can see where that's coming from, okay? And you can see this is for beams and frames. We're going to do this here in a little bit in here, okay? These are some elementary formulas, which we'll talk about a little bit later, okay? Then we look at stability and determinacy classification of structures, right? So, for example, let's take this right here, okay? So the way that I've been showing you is I've been having you compute like an I value, which is m plus r minus 2j, or m plus, you know, so on and so forth. Instead, what the FE manual is doing is it's saying, why don't you just compare m plus r and 2j. So for example, if m plus r equals 2j, that means the structure is determinate, right? If m plus r is bigger than 2j, that means that there's more unknowns than there are knowns, and it's indeterminate, and so on and so forth. But the other thing I wanted to point out is that the manual actually doesn't even list the I sub e term. So basically all it does is I sub t and I sub f, and all it's doing is you're doing the same thing, comparing unknowns to knowns, etc. So it's the same thing, it's just presented just a little bit differently. And so this other stuff that you'll see in the structure section we'll talk about later in other courses. So yeah. Okay, does that make sense? So I kind of wanted to pull that up just so that you saw, just had a quick overview as to what's given. If you have not yet started an NCEES account, I strongly suggest that you do so, because you can download the FE reference manual for free. And I strongly think that just knowing what's in the manual, knowing how it's organized, what's in it, what's not, can make the exam go a lot smoother. So it's a worthy download. Okay, so how does an internal hinge affect the construction of a shear and moment diagram? The short answer, it doesn't, okay? A shear and moment diagram is not affect the construction. The process of constructing the shear and moment diagram is not affected by the presence of a hinge, okay? And I want to be very clear on that, because I can't tell you how many times I've given shear and moment diagram problems on exams with hinges, and students are sort of coming up with forces that are supposed to be there that aren't there, okay? The presence of a hinge is something that you really should ignore when you're constructing the shear and moment diagram, but that doesn't mean that it doesn't play a part, okay? Here's the deal, okay? If I have a beam that has a hinge at a given point, I know that the sum of the internal moments at that hinge are there we go, 0. The sum of the internal moments at the hinge are 0. Okay? I use that fact in order to compute the reactions. Okay? So what I'm getting at is, if you have correct reactions, you will generate a proper shear and moment diagram. And how do you know that they are correct? Well, the shear and moment diagrams will both start at 0 and end at 0. Okay? The integral of the shear diagram should start at 0 and end at 0 on the moment diagram, like the sum of the areas, unless there's a concentrated moment. But if you've done it correctly, what should happen is your moment diagram, where the hinge is, it should cross 0, because there are no internal moments at the hinge, okay? So you're going to use the fact that there's a hinge there to compute the reactions, and then you're going to ignore it, okay? And to explain that, I have an example that we're going to do today. So we're going to look at this example, okay? So we're going to draw the shear and moment diagram for this beam, okay? I have support A, I have support B. I have a hinge right here, okay? I am going to use that hinge in order to solve for all of my reactions. But once I've got reactions, I'm going to ignore that hinge. That hinge doesn't matter anymore, okay? Now, how many unknown reactions are on this problem in total? What are the total number of unknown reactions?
4.
Say again?
4.
4, okay? So what do I have? I have a vertical reaction here, which we'll call AY. A vertical reaction here, which we'll call BY. A moment reaction, which we'll call MA, okay? Now to be clear, I am assuming directions for these things, so we'll just assume all the vertical reactions are upward. We'll assume that my moment is counterclockwise, okay? If I get a negative answer, just means I assumed incorrectly, okay? Now, there is a fourth reaction. There is a horizontal reaction at A, right? But I do know that the sum of the forces in the x direction are 0. That tells me AX is 0. Okay? Let's see if we'll drag this up here. Okay. Is everybody with me on this so far? Okay. Now, if I sum forces in the y direction, all it's going to tell me is that AY plus BY equals like whatever I have going down. And if I sum moments at A, I'm going to have this generating moment, I'm going to have that generating moment, so I'm not going to isolate any of my reactions. I propose that whenever you see a hinge, you should think about breaking out the samurai sword or lightsaber, which is what I'm going to do. I'm going to cut a section right through here. We'll call this section 1-1. Okay, so I'm going to break out the samurai sword or lightsaber because I'm a sci-fi fan. Okay, now, you tell me, would you like me to cut a section and look to the left or cut a section and look to the right? The right. The right just seems easier, okay? So that's exactly what we're going to do. Okay, and just so everybody's aware, I kind of cheated because if you look at my notebook, I copy and pasted the beam again. So I'm going to drag this down a little bit so that it's out of the way. Okay, but we're going to cut a section and look to the right. So when we cut a section and look to the right, here's what we've got. We've got a beam like this. We've got a distributed load like this. I have a vertical reaction right here, which we'll call BY. And then this part right here, That's where I cut the section. Okay? So again, all I'm doing is I'm literally drawing everything on this side of the beam. Okay? This dimension here is 20 feet. That's 20 feet. And then this distributed load was 3 kips per foot. Okay? So there's that. Now, remind me, when we cut a section through an arbitrary point in a structure, we have at most 3 unknowns. We have an unknown axial force, an unknown shear, and an unknown moment. Okay? So the axial force, I'm going to draw that sort of like this, although we're not going to solve for it. The shear, if I cut a section and look to the right, which way is positive shear, up or down? If I cut a section and look to the right, positive shear is upwards. There we go. Is there a moment here? No. And why are you shaking your head no? Because you're at a hinge. Okay. So, you tell me what to do. What should I do? Tell me what to do. This is our section.
Sum the forces in the y direction.
Sum the forces in the y direction. Okay, we are going to do that a little bit later. Okay, because, okay, why did we cut the section at the hinge? Because what do we know about the hinge? The sum of the moments are 0. So we're going to sum forces in the y direction, but we're going to sum moments first. Okay? Now, this distributed load, I'm going to collapse that into a point load. How much is that point load? And then from the section cut, how far is that? 10 feet. Okay. So here's what we'll do. We're going to sum moments at the hinge looking right. I mean, that's essentially what we're doing here. We're summing moments at the hinge looking to the right. I'm actually going to drag this over here a little bit. Okay, so tell me what to do. If I'm summing moments here, do I consider P or V? Okay, what do I have? Does the 60 generate moment times the moment arm of? Left or right? Which side?
Left.
Left. So 60 times 10 has got to equal something times 20, right? So 60 kips times 10. You all can probably see where this is going. What's BY?
30.
30 going up. That's right. Now, I want to go back to something that you mentioned, though, and that is summing forces in the y direction. Okay? We do not need to do that for the purposes of this problem, but I am going to do it anyways because I want to show you something that we're going to see later. Before we go down the rabbit hole, if I were to sum forces in the y direction for this free body diagram, I mean, let's be clear, I know that this is now 30 kips. Summing forces in the y direction will yield what quantity? Well, I'm talking about what variable? V, right? I would be solving for V. I don't need V to compute the reactions. I don't need it. But I'm going to do it anyways because you're going to see that it pops up later. So let's do this. Okay, so let's sum forces in the y direction. What do I have going up? I have V, and I have Vy equals 30 kips, right? So V what do I have going down?
60 kips.
60 kips. I don't want an arrow. Okay. So V plus 30 kips is 60 kips. V is positive 30 kips. Now remember, this is an internal force, and I'm not so much choosing or assuming a direction as I am adopting a conventional approach. Like this is the standard sign convention for shear. So I'm going to go ahead and just say it's positive 30. Okay, is everybody with me on that? Okay, so I want to keep this in the back of our heads. For later. Okay. Again, we don't need this quantity. We don't need it. It's just something I'm doing off to the side. But it'll show up later, trust me. Okay. So, tell me what to do now. You tell me, what do I do?
Construct the shear. Oh, wait, no.
Ha, okay. Okay, so let's talk through that, okay? So ultimately we want to construct the shear moment diagram. We can't start that right now, right? Because if we go back to the original structure, we know this reaction, but we don't know these two, okay? Now let's go back to the very onset of this problem. How many equations of equilibrium were we afforded at the beginning of this problem? Not 3, but 4. We know the sum of the forces in the x direction equals 0. Let's just sort of write them down here on the board. So we know that sum of the forces in the x direction is 0, sum of the forces in the y direction is 0, sum of the moments about any arbitrary point is 0, and the sum of the internal moments at the hinge is 0, right? We've used this one. We've also used this one because we know that this reaction equals 0. So we use this and we use this. So that means we have these two left over. Is there any strategy here? Do we have to do one before the other? Not really. Yeah, not really. The only other thing I might look at on the structure as a whole is I've got this really, really big distributed load. It's 3 kips per foot over a distance of, how long is the beam? 50 plus 10 is 60 plus 20 is 80. 3 kips per foot over a distance of 80 feet. What's 3 times 80? 240. So maybe what I'll do is I'll collapse this entire load into 240 kips. How far is that from A? 40 feet. Okay? And then keep in mind, we now know this. We know now that's 30 kips. Okay? So just, let's see, maybe I'll put some stuff here on the board just to prevent a massive amount of scrolling here on the screen. So we have the sum of the forces in the y direction equals 0. And then I'll repeat this on the screen here in a second. So what do I have going up? I've got AY going up. I've got BY is 30 kips going up. What do I have going down? 240, 90. Does that make sense? What about summing moments? Where would you like to sum moments? What would be the easiest place?
A.
Maybe at A? Okay. So, what do I have there? Do I have to consider AY?
No.
Because it goes right through there. But I do have MA. I got to consider that. I've got to consider tell me what, do I have to consider this? Times the moment arm up?
40,
Do I have to consider this? Times the moment arm up?
15.
So 240 times 90. So there's that. Anything else I'm missing?
Why is the 240 times 90?
Yeah, it should be 40.
Is that, oh, that's a really, yeah. You're right. I think I was getting ahead of myself thinking of the next 90. Am I missing anything? I am missing something, by the way.
BY.
BY, so I have BY of 30 times the moment arm up,
80.
80. Okay. So now let me, in a very boring fashion, regurgitate that here on the screen. So we'll say here, I'm going to drag this down. Or I'll leave it there, just so it's a little bit in view. So we have 240 and 90. Then AY, BY is 30. $240 and 90, that's what, 330? So therefore, did I get that right? Yep, I think I did. So we have MA and then this is 240 times 40. So let's see, this is 2400, this is 9600, this is 4500. So this is, let's see, 14100 equals MA plus 2400 foot kips. Therefore, MA is, what do we get? Is that 11,700? Like that. Is that okay? Is everybody okay with that?
It's quite large.
That's a big, yes. That is a very large bending moment. It's also an 80-foot long beam with 3,000 pounds per foot. So think like every foot has a Honda Civic on it. That's, I mean, right? That's a lot of load. I mean, but let me also say something. Part of, I think, the skill that you should develop as civil engineers is, like, do the numbers make sense when it comes to your intuition and engineering judgment? Yes, this is a big number. Look at these loads, though. They're really big, you know. So does it make sense? So yeah. Okay, everybody okay on this? Oh, we're doing great on time. Okay. Now, let's look at our shear and moment diagrams. Okay, so like I said, I'm cheating a little bit because I have, you know, the beam up here. Okay, what I'm going to do is I'm going to copy down the reactions. So this was 30 kips. This was 300 kips. 11 700-foot kips. Okay. I want to have a lot of room here on the screen. There we go. Okay. All right. I want to be clear that, well, let me just say two things. This distributed load, you know how we idealized it into a 240 kip load? We did that for the purposes of computing reactions. Now that we're back to drawing the shear and moment diagram, that 240 kip load, that doesn't exist. The big thing I want you to recognize is that from here on out, do not use this at all for the construction of the shear and moment diagram, because the reactions that we computed already satisfy this, okay? And you'll see what I mean when we start getting into it. So tell me what to do. We start at 0. Tell me what to do.
You go up 300.
Go up 300. Okay. Now I'm going to put some labels here. We'll call this C, D. What happens from A to C?
It goes down 150.
So if I'm at 300, go down 150, I'm at 150, right?
Yep.
At a slope of 3 kips per foot. So, oh. Okay. That's at 150. Now what happens right here?
You go down 90.
Go down 90. Okay. Which puts me at what? Okay. Now again, that point D, we're going to ignore it. It's just a point on the beam. Think of it as a point of interest. So what happens from C to B? How far do we go down? 90. So if I'm at 60 and I go down 90, what does that put me at? And then that's going to bring me back up. So that's going to look something about like this. Does everybody see that? Okay, that's your shear diagram. Now that the shear diagram is constructed, I do have a question for you. What's the shear right there? 30. Now how do you figure that out from the diagram? Well, you're at 60, right? You drop down 3 kips per foot for a distance of 10 feet to 30, so 60 minus 30 is 30. Why does that matter?
That's what we got up at the top.
Remember this? At the hinge, the shear was 30. Like I said, did we need it? No, we didn't need it, but did we use it? Oh yeah. We used it to verify our answer. Okay. All right. Let's calculate some areas. Okay. What's the area of this big old trapezoid right here? What do? We take the average of 300 and 150 multiplied by the distance, by the width. So what is that?
$11,250.
Positive 11,250. Do I have a second?
Yes.
Okay. All right. Let's take a look at this right here. Okay. So let's take a look. Let's see if we can make sense here. And this is the scales here are a little bit off, okay? So I want to look at this triangle and this triangle. The really tiny triangle. But we go from 30 to, oop, that's negative 30. That's negative 30. So over a distance of 20 feet, we go from 30 to minus 30. So how wide are each of these? 10, right? Because we go from positive 30 to negative 30 over a 20 foot. This is 10, right? So this is 10 feet. This is 10 feet. So if we want to do some areas here, okay, what do we have here? This triangle is 1/2 of 30 times 10, so this one's going to be minus 150. This is plus 150. So these two areas sort of cancel each other out. What about this little trapezoid right here? How do I calculate the area? Average of 60 and 30. The average of 60 and 30 is 45. What is 45 times 10? 450? Is that okay? Any questions on this? I mean, that's your shear diagram in a nutshell. I want to wait for a sec before we move on. I want to make sure this makes sense. Everybody okay with this? Everybody good? Okay, now, like I said, from shear to moment, ignore the hinge. Okay, by the way, what is the sum of the areas?
11,700.
So that means that concentrated moment there at the very beginning is going to be a drop downwards. Okay? So, this one's probably going to be way off scale, but the values will make sense. Okay, so we're going to start at 0. Negative 11,700. Let me do something real quick. Okay. Would everybody agree that every one of these sections of the shear diagram are linear with a slope of 3 kip per foot, or negative 3 kip per foot because it's going downward? Which means that the moment diagram, every section of the moment diagram is going to be what? Parabolic? Everybody okay with that? So, let's go from A to C. So if I'm at negative 11,700 and I go up 11,250, what's that going to put me at? Negative 450. So, like I said, the scale is going to be way off here. But maybe what we'll do is we'll do... Now, is that going to go like that? 1, or like that? 1. So... Okay. So what's going to happen from here to here is it's going to be another parabola, right? It's going to be another parabola from here to here, and it's going to go like that and like that, right? So, I mean, what happens from here to here? We go to 0, right? So, maybe what I'll also do is have a little line right there. And a line right there, just to sort of illustrate what we've got going on. So this is going to go across 0, maximum back down to 0. And this is going to be plus 150, back down to 0. Does everybody see that? So we're at 450, go up 450 to bring me to 0, then plus 150 minus 150. Does everybody see that? And then this is quadratic 2. Why is it so special that the moment diagram is 0 right here? Because that's where the hinge is. Like I said, okay, once you get your reactions, the idea is that you ignore the presence of it. Because if you do it correctly, if you've computed the proper reactions and taken into account that equation of condition, your moment diagram will cross 0 at the hinge, which it should. I mean, that's what these reactions are. These reactions are the magic values of AY, BY, and MA such that this is satisfied. Okay? If anything, I'm really encouraging you to do it this way because if you compute the correct reactions and you ignore the presence of the hinge when constructing the moment diagram, it will serve as a check that those reactions are correct. Because you're drawing the moment diagram and it should cross 0 right there. That's sort of what I'm getting at. Like, ignore it and see if the answer works out the way that it should. Does that make sense? Any questions? All right, I got a practice problem for you. Little practice, one moment diagram, not 2. I got 1 moment diagram for you that's due on Wednesday. And then on Wednesday, we will have our final shear and moment diagram lecture. I will also tell you this, just so that it's all on the same page. I am giving you a homework on Wednesday that is due the following Wednesday, not the following Monday. But do you have something due the following Monday? Yes. You have your project. You all could knock that project out in the space of like an hour. Like, I really strongly suggest you do that project before you go on October break. But, I mean, I'm not telling you to, but I'm saying I don't want you to have to deal with this class over break. You have a break, take the break. But do your project. So, that's all I got, everybody.
I can win for second place, but first place is that.